Okay, so it's 6:30 in Lagos, and I found out about something called Conway's Game of Life last week, and I thought I'll do like a short implementation of Conway's Game of Life in Python. Yeah, these are the rules. If you don't know what it is, these are the rules of Conway's Game of Life. You have a board, can be an infinite board, a fixed board, any type of board, and it has cells in the board, and in that board, live cell any cell that's alive with two or three live neighbors survives, that it moves on to the next stage of life in the next cycle of life on the board. And then any dead cell with three live neighbors becomes a live cell. Any dead cell with three live neighbors becomes a live cell, so it becomes alive in the next stage. Any other live cells die in the next generation, that's the next cycle of life. Similarly, all other dead cells stay dead. So I'll just keep the rules up here and start. Um, just so I don't mislead anyone, this is I already sort of attempted this before, but I didn't get up to uh fully I didn't get to finish. I just um was able to do the board and uh figure out how I wanted to implement the cells. But other than that, um I've basically never done this before. So let me get started. So first, I'm going to create a board class. Define in it the structure. Uh, so the board will have a width and a height, fixed width and height. So basically, when you initialize it, you have to initialize it with a fixed width and height. I've still not figured out um, how to do an infinitely wide and long board. I've still not figured that out. So this implementation is going to use a fixed board. If you have if you know a method to do this with a that's the board expands as you go, you could just tell me in the comments. Let's see. Let's see. Self dot width, and then self. And then you need a way to specify what cells are initially on. So the way Conway's Game of Life works is some cells are initially on. You give it a sort of seed state, and then all other states are continued from the initial seed state. Um, so this argument on values is going to be uh the initial seed of values on the board. So let's go self. So you need a way to I'm going to set everything on the board. So I think I should use numpy. Let me see. I'm going to use numpy for handling the board. So I'm going to treat the board like a matrix. Let's see. I plus 1. So I'm basically applying creating a zero matrix with numpy, applying the width and height to it plus 1. Basically what I'm doing is making sure there's a padding around the entire board of 1. So we type equals int. Yeah. uh yeah, so I need to check that each value is I need to check that each that the seed values don't exceed the width and height of the board. So I'm going to um, specify the maximum. I'm going to check for the maximum um, value in the seed values. So let me just show you how I'll do that. Values, and then I check for the maximum. This is an inbuilt function in numpy, by the way. Let's see. So I create an array out of the on values and check for the maximum value in that. So I make sure I now check that the maximum value is less than or equal to the height of the board. Yeah. Next, we to make sure that you check for an assertion error. Then print a message. Let's see, one of the indices of your on values exceeds board height, maybe. I don't know. Or since this is on height, you can see one of the y indices or in your on values. Yeah. So then to exit the program. So then to try again for to assert that the on values one, basically checking that is also not greater than the width of the board. So yeah, so but in this case now, that means like if you wanted to do only square boards, you can basically just use one of these. You don't need to check for the both if you're going to do only square boards. But I'm doing I think I'm going to do any type of board. Then it prints the same message again. Board width. Okay, and then it can exit. So yeah, for I in on value. So now I'm going to check. I'm going to fill in all the on values, all the cells with an on state into the board, and make sure the board has all of these cells set to a state of 1 for on, and the rest will be set to a state of 0 for dead. Let's see. Self deploy. Hi. Then once it has filled it in, I think we can print out the board just to be sure we have the right thing. So the board empty, and then maybe just an extra space for good measure. Yeah. So before we go ahead to test this, let me set a string method for my class. and that just returns the board itself, and then self the board np. Yeah, so I can go ahead to test this now, see what's up. Yeah, just gonna write out a board. Test out the board, call something demo board, go to board, give it some values, the width of 5 by 5, make it a 5 by 5 board. Then so the on values are just a set of coordinates that are on the board, so I'm just giving it a bunch of coordinates. Let's see, these are just random coordinates, and just to make sure the board actually works. So once it's done, we can test that out here. Hopefully, you should print out a board with values filled in. All the other values should be 0, but oh, I think I typed something wrong here. Oh yeah, alright, check again. All the other values should be 0, then some should be on. Yeah, we've gotten it. So you can see here some values are on, and then 3 values are on, and then the rest are 0. So yeah, so back to the code. Let's see, we've done the string method. Just do on. So this is basically a method that will check which elements on the board get to live on to the next generation, which cells on the board get to live on to the next generation. So yeah, check the length of the array. You'll receive, what it'll do is receive a cell coordinate and check that cell coordinate on the board and check for the neighbors of the cell. So yeah, self.sub. Yeah, actually first let me do a method that that updates the entire thing. Okay, so from here let's get to a method that updates the entire board. Say self, all it needs is a view of the board and get tuple. So what this is going to do is window through the board, a 3 by 3 view of the board, and just convolve through the board. And this is the reason why we set the width and height with a padding of 1, so it can convolve through. Say we put 5 and 5 here, it can convolve through the board without worrying about going out of the edge. You see what I mean in a bit. Anyway, so subtract self board np the shape. Yeah, so give it the shape. yeah. Yeah, so then it takes, am I missing a bracket? Oh, okay. I am missing a bracket. Oh, here it is. Let's see. Okay, just try it. Give it how much to move by on each after each check. Um, P. The solution to do this convolution I found in numpy's stride tricks library, because it was very tricky for me to figure out on my own. So yeah, anyway, so I got to np.live. Yeah, stride tricks. I think this should be the correct thing. Let's try it. Yeah, anyway, then we'll have something to store the board states locally, so it doesn't we just copy the board states. Okay, I should import copy from here, from C, from copy, import deep copy. If you don't know what deep copy is, it basically allows you to copy the value of a variable instead of copying by reference. Yeah, this is the way to do it in Python. So yeah. Let's see. So we copy the state of the board, the way the board is at that moment, and we now check the board states with then for I in range set the height -1. Then we then set conditions. This is a method I'll write later. We basically ask this function if this cell should live on. We're basically checking all the cells in the board and then passing the cell to this function and asking the function if the board should live on. So the way I'll implement this is the board just the function just checks all the neighbors and counts how many neighbors there are, and according to the rules, if the board is alive and has 2 or 3 live neighbors, it survives, and if it's dead with 3 live neighbors, it becomes a live cell in the next generation. So I think that should be easy enough to do. Okay, so if we pass it to the function and it returns true, we set the board state to 1, and if we pass it and it returns false, then we set the board state to 0. So we're basically asking if the board should live on. So once that's done, so the reason I copied so I think it's becoming evident the reason I had to copy the value as I save the state of the board before um, before moving on to the next, before checking, because we're basically changing the board as it is, and once the live on function checks and we've changed the original state of the board, then it means for every check, for every cell it checks, the state is actually changing, and you don't want that to happen. You want to check it against the state of the state of the current state of the board, and you want to preserve the current state of the board. So anyway, we just write that live on function now, the method rather. So do def live on, then self, and then it receives the coordinates of the cell. So it checks the window, that window that we got from over here. It checks the window and yeah, set this to non-zero. Then transpose the entire thing. Let's see. Then if self the board, and it checks against the original board. And the reason we're checking against the original board is because this board state is where we apply the changes to the board. So if you change this one, if you change this one, that means the number of neighbors is constantly changing, and you don't want that to happen. So yeah, if set the board maybe so 0 1 is equal to 1. So basically we're checking if the board is in an on state, and on is equal to minus equals 1, so we decrement it by 1. Let's see. Then if we decrement the number of on states by 1, and then if the board, because it will also count the cell as part of its, as part of the you don't want it to count the cell is checking as a neighbor, so you want to remove 1 if the board is, if the cell is on. So check if it's on, and the number of neighbors is equal to 2. Number of on neighbors is equal to 2. If it's equal to 2, or it's on is equal to 3. Actually, let me just check if live cells are 2 or 3. Yeah, if it's equal to 2 or it's equal to 3, then we return true. That means it should live on to the next iteration. But if it's if, let me just copy this. Let's see. Well, if the board is dead, if the cell is dead and the number of neighbors is equal to 3, then it should also become alive in the next iteration. Else every other thing, if it's any other in any other states with any other amount of neighbors, it should return false. Yeah, so it's basically what our method does. Let's see, then we'll check and set the board and copy the value of the temporary copy we made before as the local copy. Yeah, so then we check if so the board any whoops. Then at this point we should just check, you can exclude this if you want, because at this point I'm just checking if the board the board is empty. If the board is empty, it's just going to fill in everything from scratch again and start the entire program on. But I want the program to go on infinitely, so even if it's a terminal life cycle, like, it should fill itself up again once all the cells die. So that's what I'm doing here. Again, you can leave this out if you yeah. Then I'll define a draw method to actually draw the board on every iteration. So let's see. So while true, so it's an infinite loop. It will clear the entire screen. So let me import OS. Yeah. So the update, then we'll call the update method. We'll clear the entire screen, call the update method. Then for all the rows for all the rows in the board, it will print all the rows basically. So basically printing the board to the screen, so we can observe the board. So just print out a space for a good measure. And yeah, so I think we can test it out now. Just move this in and set an if main, and just make sure it works before I add in tkinter. Then draw. Need to call the draw method. Okay. Yeah. Oh, change this to 0.7. Yeah, and yeah, it works fine actually. It works perfectly fine. It works perfectly fine. This one would have one neighbor, so it would die, and then on the next iteration this one would have just one neighbor because they both have one neighbor on this iteration. So it's a continuous loop, but this one never dies because it's always surrounded by no, this one dies and it probably gets filled up again because we set it to fill up after a while. If I set this, if I remove this, let me see if it dies. Yeah, they all die. So at that point they all die. So the board can't sustain itself. Yeah, so I think we should start working on adding tkinter in. Or first, let me try adding some more coordinates, just to liven things up on the board a bit. Then check it out again. Yeah. These are just a bunch of random coordinates, but I'm not sure it sustains itself. I feel, oh yeah, it doesn't sustain itself, definitely, because I have this set to on. I have this on, but yeah, that's all fine. We should get to integrating tkinter to view the way the thing moves right now. So the way I'm going to integrate tkinter into this is I'm going to run the numpy board on one thread, and I'm going to run the tkinter because tkinter uses a main loop of its own, so you won't be able to just update the board in general while tkinter is running. So why is this doing this? Oh wow. Yeah. Tkinter import. Oh yeah. Let's see. By the way, I'm not so good with tkinter, so if you see I'm doing anything wrong, just let me know, because I mean, I'm not like the best with tkinter. So yeah, set root tk here. Then we can use I don't know, maybe 600 by 400. Cool number. Then we will set up a list to hold colors that we want to use, and black. I mean, there's no need for a list actually, but like actually no need for a list, but we'll see. And the demo board, then we'll set up a list to hold all the, I'm going to draw the boxes, the grid with buttons, because that's basically all I know about in tkinter. So yeah, don't shame me. And then for j in range, let's see the width. So it's going through the width and height of the board, and just getting it row by row. You'll first get it row by row, put it in B, set B equal to that, and then append it to button. So button equal to button text, nothing in the buttons, equal to 6, height equal to 4. because I set the resolution to 600 by 400. Then B, the append. Oh, we haven't even done the layout management. Grid row equal to 1, then equal to I, and the column equal to J. So basically giving it the same coordinates as the cell we're looking at. See button, so we append everything, all the buttons to React. We append the button to B, then once we have all the buttons, we append them. We append B to buttons. Then we reset B. Then we turn this into a numpy array, just because I feel numpy is faster than regular lists for most things I want to do, except appending. Let's see. Then I think we have to set up a thread for drawing, so we'll call this draw. Threading dot thread target equal to demo board dot draw. Yeah. Then we make it a daemon thread. Daemon equal true. Then we start. Then we start the entire tkinter application. Now the cause I think we need to also update. We need to update what's it called? We need to update the board each time, the tkinter board colors. So I'm going to do that in the draw methods. For J and I. J.configure background equals white. Yeah. Then another for loop for I in MP array. Turn this into an MP numpy array. That's the 0. Check for everything that is not 0 in the board and set them to white. So everything that's black, we'll set it to white, and everything that's not black, we set it to white. So basically what this does is sets everything to white, and then the rest of the stuff that's not in a dead state, we set it to black. So transpose yeah, my brain is sort of glitching. Let's see. Oh, then buttons I1, then configure all of that to be black. Yeah, then if it catches an index error, I'm not sure if this is necessary, I'm not too sure, but whatever. Pass Yeah, I think the entire thing is ready for testing. Not sure. Let me see. I think I ran into an error here. Let me see. Indices. Oh, yeah. Okay. Run it again. Yeah. So I think it's updating too slowly. Let's set this to 1. Start the entire thing again. Uh, new. Yeah. So here's the tkinter screen, and here's how it looks. Fully implemented, but like I said, it isn't an infinite board because I'm still not sure how to implement a generative board because I'm using tkinter. But if you know how, just let me know. So if you notice, it's mirroring what's the numpy array is. So um, yeah, pretty simple, and yeah, that's it.